So this would be the third video on physics chapter 2, electric potential and capacitance. Now, so part 3. Okay, this is the third part. This is the video part 3 on electrical potential and capacitance. Here in this topic, in this video, we are supposed, in this class I mean, we are going to discuss about electric potential due to a hollow conducting sphere of radius capital R. Okay, and you want to find the electric potential at a distance small r. At a distance, you are taking that point at a distance of small r. Okay, from the center of the sphere, or from the center of the hollow sphere, from the center of the hollow sphere. Okay, so when you talk about a hollow sphere, you just consider a hollow sphere and then you give some charge. Okay, hollow sphere ittalubi, and you give some charge, then all the charge will go and uniformly distribute on the surface only. Okay, the charges, they will not accumulate at the center. Okay, you take a hollow sphere, you give some charge, then all of the charge will uniformly distribute on the surface of this hollow sphere. Suppose instead of hollow, you take a solid conducting sphere. You take a solid conducting sphere and you give some charge. Okay, you have given Q charge. Then all of the charge will just uniformly distribute all over the surface only. No, the charges, they will not accumulate at the center. Okay, they will accumulate uniformly all over the surface of this solid sphere. Kali surface di accumulate koriboni, bitor di nathakiboni. All right. That is experimentally verified. Okay, take a solid sphere, give some charge, then that charge will uniformly distribute all over the surface of the solid sphere. For a conducting, okay, solid sphere, or for hollow sphere, okay, it can be conducting or non-conducting, and for the solid sphere, it can also be conducting or non-conducting. So hollow conducting sphere, hollow non-conducting sphere, data, and then solid conducting sphere, same expression, same phenomena here. Okay, you give some charge, then the charge will just uniformly distribute only on the surface of the hollow conducting sphere, hollow non-conducting sphere, or solid conducting sphere. Are we getting me? Okay. So the expression for a hollow conducting sphere, electric potential due to a hollow conducting sphere, hollow non-conducting sphere, and solid conducting sphere, it will be the same, because the charges will be accumulated uniformly only on the surface of the sphere. Is it okay? Yeah. So if you are asked to find the electric potential due to a hollow conducting sphere, or hollow non-conducting sphere, or solid conducting sphere, the expression will be the same. Okay, the same expression holds for hollow conducting, hollow non-conducting, then solid conducting. So the same expression holds for each of these three. Okay, so any question comes from this tree, you're going to write the same thing, because the charges will be uniformly accumulated on the only on the surface of the sphere. Alright. So what I'm going to do is, in the first case, okay, just do like this. You take a hollow conducting sphere, okay, and you give a charge Q, okay. Then all the charges will be uniformly distributed only on the surface of this sphere. All right. Let O be the center of the sphere and the radius of the sphere given by capital R. You want to find out the electric potential at a distance small r from the center of the sphere, right? So there can be two cases. Case 1, if small r is greater than capital R. Now there can be several cases. If the small r is greater than capital R. Second case, small r is equal to capital R. If small r is greater than capital R, then the point P will lie outside the sphere. Correct? If small r is equal to capital R, then the point will lie on the surface of the sphere. Correct? And if r is smaller than the radius, if the distance small r is smaller than the radius, then the point will lie inside the sphere. Is it okay? So we have to consider all the three cases. Now you take a point P, which is at a distance of smaller from the center of the sphere. Okay, here we're assuming that the distance small r is greater than the radius. In that case, point P will be outside the sphere. Now, the electric field at this point P, due to this sphere, will act radially outwards, right? In this way, correct? Now, you have given a charge Q, then this charge will uniformly accumulate only at the surface of the sphere, right? So the electric field at this point P, due to this sphere, will be directed radially outwards. It is from that we have studied in the first chapter. Electric field due to a positive charge acts radially outwards. And what will be the expression of E? Electric field at a point due to a charge Q will be 1 by 4 pi epsilon naught into Q upon R square. You can take 1 by 4 pi epsilon naught to be K only. No? That is alright. No problem. If you don't want to waste time writing this one. So this is the electric field at this point P due to this sphere having charge capital Q. No? Now, from the definition, the relation between electric field and electric potential is given by what? What is the relation between electric field and electric potential?
Electric potential is minus.
Yeah. Del V is equal to minus of integration E dot dr. Dot product of E and dr, right? Now, we want to find out the electric potential at point P. Del V means electric potential difference between 2 points. So electric potential difference is equal to minus integration of E dot dr. Now if we want to find out the electric potential at a point, in that case you have to consider the other point to be at infinity. So electric potential difference between at P means you have to consider one of the point to be at infinity. So del V I can write Vp final potential minus initial potential. Is it okay? Yes. Which is equal to minus integration of E, EFE, 1 by 4 pi epsilon naught into Q upon R square. But before that, this dot product has to be converted into scalar product. Now this is your electric field which is acting in this way. Okay, dr is your displacement, small steps taken as you are moving the test charge from one point to another point. So dr is also along the same direction. Is it okay? See, and I told you that since we cannot bring the charge from infinity to P, so what will we do? We're going to take it from P to infinity. So as you are taking the charge from P to infinity, okay, without changing the kinetic energy of the test charge, or without changing the speed of the test charge, okay, force equal and opposite to the electrostatic force has to be applied. That is what we have discussed in the previous classes. Okay. So as you do that, as you apply the external force, test charge can be brought from this P to infinity by taking small displacements, each of which is dr. So dr and E, they are in the same direction. So angle between them will be 0 degree. Got it? Now I need not go back to that, okay? Then this will become E dr cos of 0 degree. We all know that cos of 0 degree is 1. And we usually assume that the potential at infinity is 0. Assumption only, theoretical assumption. Otherwise, we do not know actually what is the potential at infinity, okay? So this implies your Vp will be equal to minus integration of E dr only, right? You are bringing the test charge from infinity to P. Now, in fusa to infinity bar P ani bole lage. Actually, in order to find out electric potential at P, you have to bring the charge from infinity to P. But since you couldn't do that, that is why I took it from P to infinity. So work done in taking the test charge from P to infinity will be minus of work done in bringing from infinity to P. That is what we learned also, right? Okay. So actually, in order to find out the electric potential at P, we have to bring the charge from infinity to P. From infinity to P. What is the distance of infinity from the center of the sphere? Infinity. What is the distance of point P from the center of the sphere? Smaller. Correct? Now, so Vp minus 0, assuming that infinity potential at infinity is 0, minus integration infinity to R. Your E is 1 by 4 pi epsilon naught into Q upon R square, and cos of 0 is 1. This is very simple. So this implies Vp is equal to minus 1 by 4 dr. 1 by 4 pi epsilon naught is constant. Q charge on the sphere is constant. There is no change. Here R is not constant. R is the variable here. Okay? So infinity to R to the power minus 2 dr. 1 by dr upon R square means R to the power minus 2 dr. And we are going to integrate it between the limits infinity to R. So your Vp is now equal to minus 1 by 4 pi epsilon naught into Q. Integration of x to the power n dx is x to the power n plus 1 upon n plus 1. By now it should be very clear. Integration of x to the power minus 2 dx is minus 1 by x now. Okay? By now you should have memorized this one. Integration of r to the power minus 2 will be 1 by r. We're applying the rule only, but or minus 1 by r, but we already know. So from infinity to r. Minus minus plus 1 by 4 pi epsilon naught into q, 1 by upper limit r minus 1 upon lower limit infinity. So the electric potential at P at a distance r from the center of the sphere will be given by 1 by 4 pi epsilon naught into q, 1 by r minus 1 upon infinity is 0. So your Vp is equal to 1 upon 1 by 4 pi epsilon naught into q upon r. So this is the expression for the electric potential at any point P when P lies outside the sphere. Is it okay? Yes. What about if the point P lies on the surface of the sphere? On the surface of the sphere, what will happen? Case number 2. On the surface of the sphere, what is going to happen?
R will be equal to R.
Small r will be equal to capital R. In that case, your electric potential will now be 1 by 4 pi epsilon naught into q upon capital R. Correct? Yes. No? Now, if you take any point on the outside of the sphere, then the electric field, just say electric field, your electric field will be continuous, no obstruction. So electric field will be continuous till the surface. Once you get inside the sphere, the continuity of electric field will change. Electric field la continuity harejago ni pitorito. Is it okay? Up to, if you take any point outside the sphere, okay, there will be electric field to tiny word ko na. Continuity of electric field, okay, remains undisturbed when your P is outside the sphere. Up to the surface, it will be continuous. Ni continuity tatakibo. Okay? But not uniform, okay? Don't think that continuity means uniform, because if you go far away, electric field will start to decrease, right? In that case, it will not be uniform. It will be continuity. Just think that electric field is a function. So outside this sphere, the electric field will be continuous up to the surface. Okay, but due to this, but inside the sphere, the continuity of the electric field is now disturbed because there was an obstruction. Just see, when you go outside, okay, at any point outside, then you can see everything around you. You can see the environment. You can breathe properly. But once you come inside the room, you are restricted in one particular area now. You will not be able to see what you want to see. You will not be able to breathe the fresh air as compared to outside. Is it okay? So the feeling that you have outside, the feeling that you have inside is different. Outside, any point you go, it will remain the same. So continue dictating. Pitor de haile ala kita ho jabo doe. Na, you will be suffocating. You will be bored. You will have no friends on the inside. Na, so obstacle ita kiba ita obstruction ita pitor de haile shido. You have come under some obstruction now. So continuity will be disturbed. Is it okay? Just like that. Electric field outside the sphere will be continuous. Okay, any continuous equal obstruction line. There is no obstruction. So electric field is continuous. But once you come inside the surface, then the continuity of electric field is disturbed because of the surface here. It was surface for obstruction you need to make iron. Is it okay? And some kind of obstruction has been offered by this surface. So once you come inside, things will not be the same as that of outside. And if something is not continuous, just electric field is a function. If a function is not continuous, there is no calculus. You cannot integrate, you cannot differentiate. Is it okay? Yes. So what I'm going to do is, okay, let me draw an appropriate figure for this, okay? Are you getting me? Now, the continuity of electric field inside the sphere will be disturbed, okay? It will not remain continuous. Suppose the electric field was like this. Suppose see, the electric field outside the sphere is like something like this graph. Okay, just an example, okay, continuity. Na graph to inagase. Holibi surface function ginado alakita hujashiniche. Curve, it's no longer a curve. Outside the sphere, just say that electric field is a curve, continuous curve. Na idu dan the surface function gina pitori jadam dido. You have since there was no obstruction, so this continuity will be disturbed and it will no longer a continuous curve now. Something like that. Is it okay? Yes. In that case, what I'm actually trying to say is, in that case, suppose this is the center, this is your radius. This time you are going to take a point P inside the sphere, right? Now, in that case, you cannot bring that, in order to find out the electric potential at P, you cannot take the other point to be at infinity now. You cannot take the other point to be outside the sphere now. Because outside the sphere and inside the sphere now, see, in order to find electric potential at P, we usually take the other point to be at infinity, which is outside the sphere, right? But since P is now inside the sphere, in order to find out the electric field at P, I need another point in which you are going to bring the test charge. Right at P, right? Now, are you following that? Now, electric field, in order to find the electric field at P, at a point, you have to bring the test charge from infinity to this point. In the first case, when P was outside the sphere, infinity is also outside the sphere, so you could easily do some work in bringing the test charge from infinity to P, okay? Or from P to infinity. But since P is inside the sphere, so, and if you take the other point to be at infinity outside the sphere, then outside the sphere, inside the sphere, the continuity of electric field will be disturbed. In that case, the other point also, you have to take, suppose this is your point P. In order to find electric potential at point P, you need to consider another point, not outside the sphere, but just inside the sphere. Just inside the sphere. Just inside the sphere means almost on the surface. Are you getting me? Now? Yes. And you have to do some work in order to bring the charge from this point to this point. Is it okay? Yes. Are you following me? Just inside the sphere. Okay. You cannot take the point outside the sphere because the electric field outside the sphere and inside the sphere is not the same. Okay? As you come from outside to inside, you are facing one obstruction surface. So because of this obstruction, continuity of electric field will be disturbed. Because of this obstruction, just an example, okay, the curve does not look like this, it's wrong. But I'm just giving an example, okay? Actually, I should have shown you the curve about the electric potential before, but it's all right now. So, okay, this was outside the sphere, right? Surface, on the surface, 1 by 4 pi epsilon naught into Q upon capital R. Now, 이래도 case 3, if the distance R is less as compared to R, this is your sphere in which a charge Q is uniformly distributed all over the surface. This is the center of the sphere, this is the radius. You want to find out the electric field at this point P now, which is inside the sphere at some distance r from its center. So in order to find out the electric potential at P, you need to consider another point, but you cannot take that point to be infinity now, because outside the sphere and inside the sphere electric field will not be continuous. But inside, if you take only inside, then inside, any 2 points, it will be continuous. Outside, any 2 points, continuous. Is it okay? But inside and outside, as you're coming from outside to inside, because of this obstruction surface, the continuity will be disturbed. Just think that this is a concave mirror. Now, a ray of light coming parallel to the principal axis from infinity. After reflection, yesterday this is okay. Convex lens will be convex lens. Ray of light coming from infinity, parallel to the principal axis, after traveling millions of miles. After reaching, due to this obstruction, continuity no hoido path to disturb disturbance in the path, not continuous. That's the best word. No disturbance in the path. Okay? Yes. No? So what I'm going to do is, in order to find electric potential at P, I need to take another point only, not outside, but you can take just inside the surface. Is it okay? Yes. All right. Then according to the relation, del V is equal to minus integration of E dot dr. Integration from, you are bringing from Q to, is it okay? Yes. So electric field, I did not discuss this one in the first chapter, but because of that I'm sorry, but itu jangan. Electric field at any point inside a hollow sphere. Okay, at any point inside a hollow sphere is always zero. Zero. Is it okay? Electric field at any point inside the hollow sphere, hollow conducting sphere, hollow non-conducting sphere, or solid conducting sphere, for these three, electric field on the inside is always zero. Fixed. Okay? Yes. Multiple choice question. What is the electric field? Okay? Inside a hollow conducting sphere. What is the electric field inside a hollow non-conducting sphere? What is the electric field inside a solid conducting sphere? Zero. Okay? Now in that case, see, del V means you are bringing from Q to P, right? So P is your final potential. Now you are bringing the test charge from Q to P. So P is your final potential minus initial potential, electric potential difference. Okay? Is equal to minus, where is Q? Where is Q? Just inside the sphere. That means distance of Q from the center will be the radius. Now, and then distance of P from the center will be R. E dot dr, E and dr are in the same direction. So E dr cos of 0 degree. Alright? So in that case, your Vp minus Vq. Vq means what? Vq means what? Where is Q? Just inside the surface. That means almost on the surface. So electric potential on the surface of the sphere, It's given, we know, we found out, right? What is that? 1 by 4 pi epsilon naught into Q upon R is equal to minus integration of R to capital R to small r e dr, right? Because cos 0 is 1, no? Let's see. Correct? Ne? E 0, finish. 0, integration of 0 is what? 0. So your VP will be equal to 1 by 4 pi epsilon naught into Q by R. That means either on the surface or inside the surface. Now, the electric potential at every point will remain constant. Equipotential surface. Such surface is called equipotential surface. Surface to lobby, inside the lobby, sabido. This is inside, any point inside the hollow conducting sphere. And this is on the surface. It is always constant. Such surface is called equipotential surface. Any surface which has same electrostatic potential at every point. Okay? So if you are asked to find the electric potential due to a hollow conducting sphere or hollow non-conducting sphere or solid conducting sphere, same thing you need to write. The only difference will be for solid non-conducting sphere. For a solid non-conducting sphere, the electric field inside is not 0. That is why it becomes different. On the outside, on the surface, up to that is same. Inside 0 no electric field. In that case, things becomes different. Is it okay? Can you make a note for this one? I think that's very simple, no? Okay, then take your time. So the next one will be electric potential due to a solid non-conducting sphere of radius r at the distance r from small r from the center of the sphere. Solid non-conducting, or they may say dielectric. I mean capacitance. When I come to capacitance, then I will discuss what is dielectric in more detail. Let me not do that now. Because small things can lead to so many confusion. In that case, your continuity of learning may be disturbed. Up to outside and on the surface, same, okay? Same. When we come inside, then continuity becomes different. In that case, on the inside, electric field on the inside of this kind of sphere is not 0. Okay. Solid non-conducting sphere, charge is not distributed only on the surface, on the entire volume. So it will not be 0. Okay. Actually, I think this one though, it's not required for you. It's not important for your exam, board exam. Ito nahibuki dia bito wala. Holibi ki obo competitive exams. Kani beshi helpful ase do ramini discuss kore. Okay. So consider a solid. Yeah, it's on. Consider a solid, non-conducting sphere in which a charge plus Q is uniformly distributed all over this sphere. Okay? O is the center of the sphere. Let's say that capital R is the radius. Case 1, if the point P lies outside the sphere. Case 1. If P lies outside the sphere, in that case, what happens? Your small r will be greater than capital R. No? P is a point outside the sphere. Then small r will be greater than the radius. Electric field at this point, due to this positive charge, no, will act radially outwards in this direction. And we know that the electric field at any point, due to this charge, the overall charge to Q, is given by, electric field at P will be given by 1 by 4 pi epsilon naught into Q by R square. That you already know. Now, we know that the relation between electric field and electric potential difference will be is equal to minus integration E dot. Okay? In order to find out the electric potential at a point, you have to take the other point to be at infinity. So electric potential difference means final potential minus initial potential. And we assume that the potential at infinity is 0 is equal to minus, here both E and dr will be in the same direction. Is it okay? Yes. So E dr cos 0 degree. So Vp minus V infinity, assuming to be 0, minus, you are bringing the charge from infinity to P. Infinity to P. Distance of infinity from the center is still infinity. Distance of P from the center is smaller. So infinity to smaller. E dr, E is 1 upon 4 pi epsilon naught into Q upon R square dr, where cos 0 is 1. So your Vp is minus 1 by 4 pi epsilon naught times Q, integration infinity to R, R to the power minus 2 dr. Integration of R to the power minus 2 is minus 1 by R. So your Vp will be minus 1 by 4 pi epsilon naught times Q, minus 1 upon R from infinity to R. Minus minus becomes positive, so your Vp will be 1 by 4 pi epsilon naught times Q. Instead of this R, we put the upper limit 1 by R and then minus the lower limit 1 by infinity. 1 by infinity is 0. So the electric potential at any point outside the sphere is this. Same. Now, if point P lies on the surface of the sphere, then in that case, if P is on the surface, then your capital R will be equal to small r. Up to the surface, electric field is continuous. So in that case, on the surface, when small r is equal to capital R, the electric potential will be given by 1 by 4 pi epsilon naught into Q upon capital R. Okay? Now let's go for inside the surface. Now this will be a little bit different. Okay, on the surface lado, on the square lado, your Vp will be 1 by 4 pi epsilon naught times Q upon capital R, right? We need to recall that. So, case 3, if P lies inside the sphere, then in that case your small r will be less than capital R. So this is the sphere. If this is the sphere, your sphere doesn't look nice. This is your sphere, 2D sphere. This one is your Q, this one is the center, this one is your radius. If P lies inside the sphere, this distance is smaller. Then in order to find the electric potential at P, okay, you need to take another point where you are going to bring the test charge from that point to this point P. But you cannot take the point that point to be infinity or outside the sphere, okay? Because the continuity of the field does not remain the same, okay? The field is not continuous on the outside and on the inside. Is it okay? As the field, okay, the field outside the sphere and inside the sphere will be different because of this obstruction. Okay, due to the obstruction by the surface of the sphere, the field does not remain continuous. But inside the sphere, at every point, the field will be continuous. Is it okay? So in order to find out the electric potential at P, you need to take another point which is just inside the sphere. Say S. Is it okay? And in order to find out the electric potential at P, you have to bring the test charge from this S to point P. Is it okay? Yes. So what will be the potential at the point S? Potential at the point S. S is like just almost on the surface. So it will be 1 by 4 pi epsilon naught into Q upon capital R, right? Now, for a solid non-conducting sphere, you have to know this one. The electric field at any point on the inside of this non-conducting sphere will be given by 1 by 4 pi epsilon naught into the charge enclosed upon capital R square times the distance. You don't memorize clearly for now. For now. Okay? For now. This relation is included in your first chapter only. Electric field at any point on the inside of a solid non-conducting sphere of radius capital R is given by this. If it is for a hollow non-conducting, solid conducting sphere, then it's 0. Alright? But for a solid non-conducting sphere, it is not 0. This is the relation. Q is the charge. Capital R is the radius. Small r is the distance of that point from the center. This you have to know. Okay? Very, very, very important relation, this one. I didn't discuss that to you earlier. And I'm sorry for that. Okay, so according to the definition, del V is equal to minus E dot dr. You are bringing it from point S to point P. Del V means potential difference, final potential minus initial potential. No? Is equal to minus integration distance of S from the center, capital R, distance of point P from the center, small r. E dr will act along the same line. So E dr cos 0 degree, correct? Okay? Yeah. Now, your Vp minus, what is Vs? Electric potential on the surface? 1 by 4 pi epsilon naught into Q upon capital R is equal to minus R, capital R to small r, your E, this is your E. 1 by 4 pi epsilon naught into Q upon R square or R cube. Oh, R square or R cube. I think it is R cube. Into Q upon capital R cube times R. It's not R square, I'm sorry, it's R cube. It's R cube. Into dr. Right? Constant sa pula ne? Vp minus 1 by 4 pi epsilon naught into Q upon R is equal to minus 1 by 4 pi epsilon naught is constant. It is constant. Capital Q upon R cube is also constant. So we will integrate only R dr within these limits. Definite integral, right? Okay. So some space is required for doing that integration. So this has to be removed immediately. So Vp minus 1 by 4 pi epsilon naught into Q upon R. Minus 1 by 4 pi epsilon naught into Q upon R cube. And then integration of x dx is x squared by 2. X R squared by 2 within R2 small r. Correct? So your Vp minus 1 by 4 pi epsilon naught times Q upon capital R will be equal to minus 1 by 4 pi epsilon naught into Q upon 2R cube. Ne? 2R cube. 2 like this. Upper limit small r square minus capital R square. Upper limit minus lower limit. Right? Small r jagade upper limit halibi, aro r jagade aro lower limit halibi. Now 2 like this should I give it?
So get negative value.
Oh, we'll see to that. Vp minus 1 by 4 pi epsilon naught into Q upon R. Multiply koribi. Let's multiply ni. Minus 1 by 4 pi epsilon naught into Q R square upon 2R cube. Correct? Minus minus plus 1 by 4 pi epsilon naught into Q upon 2R only. R square and R square cancels out. Right? It will be jawab ne. Vp is equal to ito plus ho jawab na 4 pi epsilon into Q upon R. This term, they are like terms C. Plus 1 by 4 pi epsilon naught into Q upon twice R minus this one. 1 by 4 pi epsilon naught into Q R square upon 2R cube. This expression has never been asked in board exam because its expression is very weird. Its result is very weird. But competitive exams too, you will get this kind of things. But when you competitive exam, you are applying for NEET, you are sitting for NEET exam, will you be able to recall all this relation?
Yeah, very poor.
Yeah, I think it's going to be very tough now, unless until you are preparing so hard. Even for me, I won't be able to remember. I cannot remember. So it will be the solve correct. Kimano? Okay, I don't solve correct. I will. 1 by 4 pi epsilon naught into Q by R command ne? From these two terms, Q by R command then 1 plus 1 by 2, 3 by 2. Minus 1 by 4 pi epsilon naught into Q R square upon twice capital R cube. 3 by 2. So 3 by 2 times 1 by 4 pi epsilon naught into Q upon R minus 1 by 4 pi epsilon naught into Q R square by 2R cube. From the whole expression, what common can I take? From the whole expression, 1 by 4 pi epsilon naught into, can I take Q by R only? Then this one will be 3 by 2 minus R square by 2R square. 2R square. No, I did not take 2 common. Yeah, we could have taken 2 common also. If you want to take 2 common also, that is alright, but I leave it here because it looks nice here. Okay? If you take 2 common, you can include with this. Don't take it here, okay? So this is some kind of weird expression, but never have been asked in your NBSC board exam. But for the competitive exam, this kind of only expressions are required. Okay? Alright. So that's it.